Hi, I'm Matt Whitaker. I am a research faculty member at Stony Brook University and a scientist at the National Synchrotron Light Source 2. And today I'm going to talk a little bit about some research that we did with a new faculty member at Penn State and his undergraduate on metals. So metals are everywhere in everyday life. No matter where you look around you, you always see them, from planes, trains, and automobiles to machine tools and the fixtures that you find in your bathrooms and kitchens at home. And most of these metals, especially the ones you see at the left here, are formed by the process of metal casting, where you take liquid metal and you pour it into a mold to form the shape that you want. Nowadays, we can do much more complex shaping and forming using the process of additive manufacturing, which is more commonly known as 3D printing. So you can form very complicated and very specific shapes and sizes of metal products. But sometimes we want metals that are stronger or fit a particular purpose. And in this case, we need to do some processing to the metals. And one of the most common processes for metals that people would be familiar with is forging. And the examples go far back in time to the blacksmiths that used to make nails, spikes, and horseshoes and things like that. And they're also used in very industrial processes today, which you can see at the bottom left here, where we're forming a large building ballast that's actually going to support the weight of a large skyscraper. So the process of forging basically takes your raw hot metal material and has an impact force that not only shapes it, but also works to recrystallize the material and strengthen it in a particular direction that is beneficial to what you want that metal to be able to do. Now, obviously, it's very important that this process is optimized in order to be reproducible, because if we're going to form something like a nail, or in the case of a building ballast, you want to make sure that it has high strength, and you want to make sure that whatever you do to it, you can reproduce multiple times so that it's the same every time. You also want to make sure that it has a very low failure rate for the safety of the people who might be the occupants of that building. We also want to be able to enhance the sustainability of this forging process in order to minimize the amount of energy that it takes to make these pieces, and we also want to reduce the amount of waste that's produced during the processing of these metal pieces. So the problem that we have is that we can see things before and after, but we can't observe what's going on while we're doing the forging process. We can't see the process itself, only the products after we've done the forging. And this is where the synchrotron comes in. In particular, NSLS2 is an ideal place for studying this. And the XPD, X-ray powder diffraction beamline at the NSLS2 has high flux, which means lots of X-rays. And those X-rays are very high energy. And both of these things are very important for being able to see through and study metal products. In particular, XPD also has a unique 1,100-ton hydraulic press that's designed for studying materials, primarily earth materials, but many other materials as well, at high pressures and temperatures. And we can also control directional strain, which I'll get to in just a moment. So to talk a little bit about pressure in relatable terms, pressure is basically just force divided by area. So if you have a block that's a particular weight and you lay it flat, it has less pressure exerted on the ground than if you stand it up on its end. It's the same force, but it's a different area, and that leads to a different pressure. That's the reason that we wear snowshoes in the winter, so that we can distribute our weight more evenly across the surface of the snow and we don't break through. On the other hand, a 100-pound woman in stiletto heels exerts 20 times more pressure on the ground than a 6,000-pound elephant. So it's the opposite of the snowshoe effect. This is exactly why I stopped wearing stilettos. That and the difficulty in finding them in size 16 also played a role in that. But anyway, so to talk a little bit more about pressure, if you hold your arm out in front of you, the air pressure that you feel right now is 1 bar. It's about 1 atmosphere of pressure. And if you take your other hand and you give your arm a tight squeeze, you're only adding less than half a bar of pressure. So not even 50% more than the pressure you're feeling automatically, just being in the room. Now, if you were to, all right, let's not go with Hulk Hogan, he's kind of dated. The Rock, yes. If you take a bear hug from The Rock, you're adding about 5 to 7 bars of pressure. So now you're about 7 times atmospheric pressure. And if Bruce Lee were still around and you did something to make him mad and he kicked you in the face, you would be experiencing 25 to 30 bars of pressure. It only takes 12 bars to break bones, so that's pretty serious. Now I'm going to move ahead a little bit further and talk about pressure in not quite as relatable terms. So if we go as deep as we can on the Earth to the deepest part of the ocean in the Mariana Trench, that's about 1,100 bars, so 1,100 times atmospheric pressure. The press that we have at the XPD beamline is able to achieve pressures that are about 250,000 times atmospheric pressure. So there's a very big range of conditions that we can cover. In particular, the experiments that I'm going to talk about today were in the pressure range from 10,000 to 20,000 bars. So to look at the experiment schematic for the high pressure experiment, what you can see on the lower left here are the anvils which will exert pressure on the sample itself. The sample sits in the middle of your pressure assembly, and the X-ray beam comes in from the right and then exits through the left. And that's how we observe the sample at high pressure and temperature. And as you can see from this schematic here, the X-ray beam actually passes in between the anvils so that it can see the sample directly at every condition of pressure and temperature that we want to reach. So we then take these anvils and put them in the press, and then the press pushes up from below in order to raise the pressure on the sample. And then we have the unique ability in this design to be able to drive the top and bottom anvils separately in order to add a deformation field of strain on the sample itself. And that becomes important, particularly when we're looking at forging processes. So let's talk a little bit about why we want to be able to look at something like this. When we have elastic deformation, your sample starts at room conditions of, say, room temperature, room pressure, and then you add pressure to it. So the sample under stress, which is the same in all directions, will make it smaller, which is exactly what you would expect. And then when you release that pressure, the sample reverts to its original shape and size. However, in plastic deformation, which is what occurs during these forging processes, we start with the sample at ambient pressure, and then we put it under pressure, but it's not the same in all directions. And then once we release that pressure, the sample is changed in the shape and properties from what it was before we put it under those plastic deformation conditions. So let's talk about these experiments that we did on the iron metal. You can see on the left is a picture of the press, and we have the incoming X-ray beam that shoots right in between the anvils there. All the way on the right, we see a schematic of where the cell assembly is, and your iron sample is right in the middle. The incoming X-ray beam hits your sample, and then we can actually use what's called a scintillator, which is just a fancy word for a crystal that lights up when the X-rays hit it. And we can use that in order to take images directly of the sample while it's at high pressure and temperature. And then you can see that there's a large panel area detector behind it that allows us to collect the X-ray diffraction data. And we'll talk about all of this in just a moment. But first, the X-radiographic imaging is the first thing that I want to talk about. And this here is a picture of our iron sample at 10,000 bars before we did any of the deformation to it. Now, it can be a little bit difficult to see if you're not familiar with looking at this. So what you're looking for is in this box right here. That is the iron sample right there. Okay? And then we pre-strain the sample by adding that deformation field in the particular direction that we talked about earlier. And we can see that now we have the iron sample at 10,000 bars with 12% of pre-strain. And you can see clearly that the sample has changed its length. And this is what we measure in order to be able to determine what next steps to take during the experiment. Now, to talk a little bit about the X-ray diffraction, what the X-ray diffraction shows us is the different crystals that are in the iron sample at high pressure. When the X-ray beam goes in, it hits all of the different crystals, and the X-rays are scattered, and they're scattered in these cone shapes that are then collected on the image detector to the right. And we can actually see some of the data in a moment. But what you're going to be looking for is, in these experiments in particular, is just as we talked about before, when we have a sample at ambient conditions, room pressure, room temperature, and 1 bar, we stick it in to the press, we collect the X-ray diffraction, and we see rings that look very similar to the ones that are shown in this diagram here. Now, we're going to add some pressure. So we're going to make the sample smaller. We're at 10,000 bars now, and that causes the rings to get a little bit bigger. Now, once we add that deformation field, those rings that started out nice perfect circles at 10,000 bars, once they've been deformed a little bit, those rings expand into ellipses. They're no longer perfect circles. And the sample is no longer the same shape as it was before we started. So this is what we're looking for in the experiment. And that's exactly what we see. So as you move from the top left to the top right, the rings go from room pressure to high pressure, and they do get bigger. This is very difficult to see with the naked eye, so I'm going to show you something that's a little bit clearer in just a moment. But then as you move from A to B, we go up in pressure, we heat a little bit, and we can see some spots form in C, and then we do the deformation, and that's where we see the ellipses form in D. So if we take those circles and we unfold them, doing a process that's called a cake plot for slicing, that's the reason for the name of it. If we then look at a perfect circle on the cake plot, this will be represented by a perfectly straight line. In particular, I want you to look at these two lines right here, which are perfectly straight lines at high pressure before we do the deformation. Then once we do the deformation, you can see that those straight lines now wiggle back and forth. And those wiggles are representative of those ellipses that start to form when we have that deformation effect. So we are able to see exactly what is going on in these processes, and we're able to replicate what occurs during the forging process. So going back to the original reason for all of this, the problem, we couldn't see anything but before and after. And we have had success. We can observe these processes as they occur at high pressure, high temperature, and with directional strain. We can repeatedly reproduce these pressure, temperature, and strain conditions that are found in forging and some of the textures that we observe in the finished products in real life. So we know, based on what we're seeing afterwards, that we're able to replicate what's going on in these materials, which is really, really important. And we found that grain growth tends to be faster and easier at lower pressures and higher temperatures, and the recrystallization process is a bit slower at high pressure with lower temperature. And the great thing about this is that it's only the beginning of the study. We have so many more things to do where we can determine other conditions of forging, and we can also look at different processes of metal formation, such as metal rolling, where we take a larger metal and we roll it into a sheet in order to produce particular properties, where we can form sheet metal, or even, like shown on the right, large pipe fittings. And we can also be able to begin to understand the extrusion process, where metal is forced through a die. And at that die interface, there's very high pressures and temperatures that are experienced, and we are able to replicate those at the NSLS2. So this is a very exciting field that we're hoping to continue looking into, and I'm going to close with a picture of my children who are much cuter than me, and these are the people whose world we're trying to make a better place with the science that we do. So thank you very much.